welcome to my class. It's for me the first time to teach a class in this university, apart from a class where I just taught one student. Okay, I taught some experiments, but this is really do more listening than doing things yourself. But I hope that you will feel very free to ask any question at any time. So please feel free to stop me at any time. That's very welcome. Now, you may wonder why in this Hot Topics in physics I bring this topic here, solar cells. Now, we could argue the sun is hot, so this is certainly a hot topic in physics. But another thing, why I think it's a hot topic for Japan is very serious. That last year, when multiple catastrophe in Fukushima and in Tohoku, and suddenly Japan as a country realized that energy is not granted. So you can't take it as something, oh, we always have energy, we never need to think about it. Suddenly everybody realized I have a responsibility for dealing with energy. And recently I read the Akuka newsletter. This is a newsletter for an Asian Christian University Association. And they featured a project of 2 students from our university working locally for the liberalization of the electricity market, etc. And I think that's a great approach. So there are people taking responsibility. And so I must admit, and so I'm in that sense I'm guilty, that I never cared too much about nuclear power and its use in Japan. I thought, okay, Japan is a highly developed country and it should be safe. Technology has a high level, and usually in Japan everybody takes care and everything's very clean. I thought it's reasonably safe, I thought. And even I lived for the last 14 years in Fukui, Hokuriku, which is the nuclear Ginza of Japan. So 15 reactors, including a fast breeder, loaded with plutonium and liquid sodium. But I thought, okay, it has always been fine, nothing should happen there. But after Fukushima, I realized, oh, this is not safe. And also, Fukui has experienced, right after the war, a big earthquake, killing thousands of people in the city of Fukui. So it's also an earthquake region. Earthquakes happen there, strong earthquakes happen there. And I listened to some TV program later last year, and a Japanese seismologist, earthquake researcher, he said the Japanese nuclear power stations, the safety container vessels, which should contain anything coming out in case of an accident, are safe up to 600 gal. And a gal, in the honor of Galileo Galilei, is an acceleration unit, 1 centimeter per square second. And they are safe up to 600 gal. So if earthquake-induced accelerations happen locally, they won't break. But the seismologists measured 4,000 gal in strong earthquakes in Japan. So all safety container vessels in Japanese nuclear power stations must break at earthquakes when they are so strong and happen really near such a nuclear power station. And so I thought, okay, the only way we can go now in the future is try to find new ways to make energy and try to become free as soon as possible of nuclear energy. okay, you can say, but France is not wanting to get rid of nuclear energy, yes, but they don't have these strong earthquakes. But I don't say that it's safe to live in France, but it's safer than living in Japan with these strong earthquakes happening here. And so certainly renewable energies are a way for the future to get kind of safe energy, which in the long term can also be paid for and can sustain the country, the economy, and everything. And so solar cells is not the only renewable energy, but solar cells is an already existing renewable energy, which is already produced in manufacturing on a large scale, so it's available and it can be installed very quickly. And therefore I thought, okay, first let's concentrate on solar energy. And next there are other energies, and Japan has some advantages with respect to other energies as well, but I'm not talking about that today. So in that sense I want to present this topic here. So let me begin then. I took some of the content from a conference here in Tokyo at the beginning of November, and one of the students here, he also attended. This was the second German-Japanese Solar Day. So mainly German research institutes and industry, together with Japanese national research institutes and industry, made a kind of bilateral day to exchange the top-level information. And so I took some of the information and slides from there with the kind permission of the people who gave me the slides. So I will talk in principle about the conversion of light to electricity. How does that work? And then I talk a bit about semiconductor physics. Semiconductor in Japanese is handoukai. I talk about what's called phonons, and then there are two classes of semiconductors. They're called direct and indirect semiconductors, and to understand that you need to know what are phonons, etc. The name is kind of similar to photons, and it has some meaning as well. Okay, then I talk about so-called multi-layer solar cells. So these are kind of advanced solar cells. And about concentrator photovoltaics, that means to concentrate light. Then I talk about thin film cells, and these are, and therefore I have to explain that, these are so-called direct semiconductors, so therefore I want to clarify that first. And then I talk about some economic aspects as well, so bring it close to reality in a sense. Okay, what is a solar cell? Now, just an easy explanation of principles. You know an electric motor, and an electric motor converts electricity into motion. But you can operate an electric motor in the other way and convert motion into electricity. So you just turn the motor, for example, even by hand or with water power, and out comes electricity. So it's a kind of principle which works in both ways. You can convert. And then all of you know the light-emitting diodes. And so what do the light-emitting diodes do? They have a semiconductor inside, and that converts electricity into light. But as you can reverse the operation of an electric motor, you can reverse the operation of a light-emitting diode. You can put in light and get out electricity. And that is then here, this form of the solar cell. So that's kind of principle and analogy. And the internal structure, though the outside they look different, but they're made from same type of semiconductors, same type of inner structure. Okay, now here another definition taken from an undergraduate textbook, which is very popular in American university colleges, and a very compact definition, so I just will read that for a moment. A silicon, that is a material, and this material is most abundant on Earth, after carbon, so second most abundant element. You can find it in all rocks on Earth. There's no question of having raw materials, plenty of raw materials. A silicon photovoltaic cell is formed when layers of electron-rich N-type and electron-poor P-type silicon semiconductors are joined. So two types of silicon semiconductors are joined. One is electron-rich, one is electron-poor. What that means, I will also show in more detail later. A redistribution of electrons near the junction, that is the interface, produces an electric field at the junction. So where the two are combined, an electric field is perpendicular to the interface. When a photon of sunlight separates positive and negative charge, so as you know, a photon can hit an atom and raise an electron out of the atom to a higher energy level, and if it's high enough, it can become free from the atom and float in a conductor or semiconductor. So you lift it from the valence band, where it is bound to the atom, to the conduction band, where it becomes free to move between the atoms in the crystal. So when a photon of sunlight separates positive and negative charge, that electric field pushes them in opposite directions. So it can push the positive charge in one direction and the negative charge, the electron, in the other direction. Those separated charges are collected and used to power an electric circuit. So that's an easy definition in terms of words of what is. Okay, now I want to show you a brief movie which explains you how a solar cell works, how the materials are joined together, how the electric field builds up at the junction, and how that can separate charges and start to power an external circuit. So that's the basic mechanism of every solar cell. So I'll switch on the slide here. And then I will continue to give you a little more details. So what you see here now is a modern solar cell. And you see what you already know. Here is the N-type semiconductor, and this green layer here symbolizes the P-type semiconductor. And then here in gray and down here you have the contacts. But on the back side you can really make contacts easily, but on the top you want the light to come in, so you make small contacts to have enough space, as much surface area exposed to the light to come in from the outside. And then you find things here, an ALD layer, and on the next slide I explain what's an ALD layer. So that makes it, with ALD technology you can make very thin and very precise, up to atomic diameter precision layers. And this is a very good cell. It has an efficiency of converting sunlight into electricity, so energy, power to power, of nearly 24%. So that's quite high. And then you find three specifications here. This is a voltage, this is a current, and this is called feed-forward factor. And I will explain these as well, what they mean, because they are the basic parameters with which every solar cell is characterized. So if you read a technical journal or so, they will always give you these numbers here. And so I want you to understand these basic numbers to get the principal idea of what these numbers mean. So on top here, you have what's called a passivation layer. And also at the bottom here, you have another passivation layer. And the passivation layer is a layer which has a function so that the hole and electron pairs cannot easily recombine. So otherwise, they just travel to the surface, recombine, and no current comes out. So at the very bottom and the very top layer, you introduce a passivation layer to stop them from recombining quickly. So this is the idea, to make it also more efficient in in that way. Okay, so the anti-reflection coating increases the light intake. So that's one way you can improve the efficiency. Then backside contacts, if you manage to put all contacts on the backside with some technology, you can get more free area which is receptive for light at the top, and you get also more light intake. Then the passivation layers, as I explained, they reduce the loss by recombination of electrons and holes on the surface. And ALD is atomic layer deposition technique. And it can make very thin conformant, that means it has the same shape like the object, which you coat, with control of the thickness and composition of the films possible at the atomic level. So you can, one atom thick layers you can deposit, and you can say stop after you have one atom thick layer or 2 or 3 atoms. It's a very precise technology. And then this is a test condition, and this is called AM 1.5, and it means a test condition at an absolute air mass of 1.5. So if the sun would come vertically at the equator onto your solar cell, you would have air mass 1. But if it comes in at an angle, as it usually comes in Japan too, at this angle here, it just has an air mass, so summing up, integrating up all the air density along that path, of 1.5. And that's a kind of standard test condition which is suitable for countries like America, Europe, and Japan, etc. So therefore this is always a decided test standard. Under these conditions you should make testing. Okay, now the first of the 3 parameters is the so-called open circuit voltage. So you have the solar cell, the sunlight comes in, but you don't add any ventilator or any light bulb or anything. It's just open. And you measure the voltage which you get here. So this is a maximum voltage possible which you can measure. You don't take out any current, you just measure like the voltage of a battery. What is the voltage here? And that's you put down in this voltage current diagram at this point here. And then you can here add resistance, and you can slowly decrease the voltage and let a current flow through. And so the current which can flow through up to having a complete conductor here is pictured here. So this is a kind of voltage current characteristic. If gradually, here you have a kind of a resistor of infinite strength, no current flows, it's completely insulated, and then gradually you reduce it, then this is kind of current that flows. And it's called IV curve, for I or J for current and V for voltage. And at this point here, you just short circuit it. So you just take a copper wire and close the 2 contacts, and you have maximum current because no resistance. And this is the kind of maximum current, and in between you have all the different values characteristic for this solar cell with this type of material and PN junction, current and voltage here. And so for an ideal solar cell with few resistive losses, this current, the short circuit current, is the same like the light generated current. So the light here comes in, generates current, and that's the maximum current that comes out. And so the short circuit current is the largest current which may be drawn from the solar cell. It's the largest possible current. Okay, but the power of the solar cell is the product of current times voltage. Okay. And so this is a product of current times voltage. If you have the short circuit current, then you have 0 voltage. So the product is 0. And if you have an open circuit, you have no current. So the product of current and voltage becomes 0 again. And in between, there is a kind of maximum value where you have the highest product of voltage and current. And this means a kind of square area here, voltage times current, and the maximum square area which you can fit in is given by this point here on the power axis. And now we can define the third entity, which is called the fill factor. And so you have the open circuit voltage and the short circuit current, and they are the maximum current and voltage possible here and here. And I think there is another rectangle here, which I hope you can see in your printed. Yes, you can see it. And this other outer rectangle here is the product of the maximum voltage and the maximum current here. And this product here, you put in the maximum voltage and maximum current. This product here, you put in the denominator here of this computation. Here also as well. So at both of these operating points, the power is actually 0. So if you are here or here, as you know, I put in here the power diagram as well, so I superimpose two diagrams, is 0. So you actually want to operate this point where the power becomes maximum. And so you have this voltage at this point and this current at this point. So the actual power which you can take out is only this area here, the area A. So the coefficient of the area A divided by the area B, the power which you can actually take out, and the kind of ideal maximum power, this coefficient, this quotient here, you compute here. And so area A divided by area B, this is this fill factor, and that's called FF. And if the fill factor comes close to 1, then it means this curve here is like a perfect rectangle here. But it's not in reality, so it shows you how much this curve is not ideal compared to a perfect rectangle, which would give you the maximum power here. And so this is the way how you compute it. And now the efficiency, you compute by taking the maximum power and divide it by the incoming power of the sunlight. And then you know how much of it is converted into the power that comes out. So here you take the product of the rectangle formed by open circuit voltage and short circuit current, and multiply it by the fill factor here. And therefore you get this big rectangle here. And then you divide it by the incoming power of the sunlight, which makes this outcoming power, and then you have the efficiency. So by measuring the open circuit voltage, the short circuit current, and by computing the fill factor, you know the maximum power which this solar cell can give, and you divide it by the incoming power from the sunlight, and then you have the efficiency. And this is just the way how you can measure things. But the underlying physical, quantum mechanical mechanisms that give you a certain efficiency are here, and I can't explain them in detail today, but in the lectures in the future, in physics, you will learn about these factors, these material properties. So the reflectance efficiency, so low reflectance means a higher efficiency of the solar cell because more light comes in. Thermodynamic efficiency, that means that not much energy is dissipated in just to heat the solar cell instead of making current. Then the charge carrier separation efficiency, so how efficiently the photons which come in can separate positive and negative charges. And the conductive efficiency, so that there's no loss because you have some resistivity inside, and current cannot flow because the conduction is not ideal. Okay. Now, to get good silicon, you want material of high grade, and there are some names for it, and you will read them in the literature. And Mg means metallurgy grade silicon. Like a pure metal, you want to have pure silicon, and that's called metallurgy grade. And it is 99% pure, and you make it by taking out the oxide. Usually you have silicon oxide in nature, And so you add carbon, you heat it to a very high temperature, and the oxygen separates from the silicon and combines with the carbon and comes out as CO2. It's the same way how you purify steel or other metals by trying to take out the oxides in the form of CO2. Therefore you need carbon to take it out. And then there's another purification process. This is a modern process. It's efficient, more efficient than previous processes. Physiochemical purification, and it makes an upgraded metallurgy grade silicon called UMG, and this is a very high purity of 99.999%. So that becomes really ideal. And this new method here, for which I can't describe details now, has less than half the price of the previous energy-intensive Siemens process. So there are big, large-scale new technologies to make pure silicon with using less energy. And that means overall for the production of the solar cells, you will use less energy, they become cheaper, and they have a quick return. So you just need to operate them half a year or a year, and already all the energy which you use to make the solar cell is delivered in terms of electricity. So high material quality improves the efficiency. And now I come to what is a phonon. A phonon is simply motion of the atoms and the electrons, and is a collective motion, like a sound wave. And here I picture just in one dimension, but actually they move in 3D space, like planes, moving planes in the crystal. And you see phonons of different wavelengths here and different frequency. And so this is imaged here, so that they can vibrate together. It's a collective vibration at different wavelengths and at different frequency. So if you just keep that knowledge, there are these phonons. And I'm sure that Professor Hiroshima, he is a condensed matter physicist, so he's an expert on phonons, etc. He can explain you all the details. Now, as it happens, silicon is a so-called indirect semiconductor. For silicon, a photon is not enough to lift an electron from an atom into the conduction band. It needs a push from the side to change the momentum and bring it to the lowest level of the conduction band. And this push comes from a phonon. So therefore in silicon, it's actually a combination of the vibrations in the crystal, which always push electrons around as well, and the photon coming in. The photon changes the energy of the electron, and the phonon changes the momentum suitably, so to really get into the conduction band. And so the gap between the valence band, when the electron is bound to a silicon atom in the crystal, and then it becomes free, floating around freely in the crystal, this gap here, this energy gap, for silicon is 1.2 electron volts. It's a unit for energy, for very tiny quantities of energy. And so the photon which comes in must have at least the energy of 1.2 electron volts. And you can take the frequency of the light wave of the photon and multiply it by the so-called Planck quantum. And that gives you the energy that is in this photon. So simply take the frequency of the light, multiply it by the Planck quantum, and you have the energy of that photon. So this photon must have a certain frequency, a certain energy, in order to be able to lift an electron sufficiently. So if you send in light with less frequency, is a lower frequency and a longer wavelength, therefore it has not enough energy to lift up the electron. So there must be a certain minimum. Yeah. And also, for the presence of phonons, you must have a certain thickness of the material, so that the phonons can develop and push the electrons around. And therefore, this step here is called an indirect band gap. This gap here is called band gap, and this is called an indirect band gap. And you have other semiconductors which do not need this phonon push, and they are called direct band gap semiconductors, or short direct semiconductors. So no phonons needed, and that means you can make it much thinner. You can save a lot of material in this way. And they are then called thin film solar cells, very thin. And now here we have a single material, a silicon cell, which you see here, and light comes in. But you see, it has a certain band gap, and the light here with short wavelengths, which has more energy, cannot deposit the energy which is higher. So the higher energy here is actually lost in terms of thermalization. So thermalization loss is excess energy of photons, which is more energy than the band gap has. It gives this energy to the electron, but it dissipates in the crystal in the form of heat. So this is lost, and therefore thermalization for photons which have more energy than the band gap. And then down here, you have photons which have a large wavelength and low frequency, and so they don't have enough energy to push electrons in the silicon because of this band gap here, 1.12 electron volts. So they are also lost. So they just go through, and for these long wavelengths photons, the silicon is a kind of transparent. They don't see it because they don't match on the band gap. So they are also lost, and therefore this is called transmission losses here. And okay, later we have a tunnel diode, so I'll explain that later. Now, different semiconductors have different band gaps, and we can use that. And here's a list of different semiconductors. But germanium is just in the periodic table below silicon, and its band gap is less. And then you have a kind of semiconductors which are combinations of two other materials, which also become semiconductors here. And they have a variety of band gaps here. And the idea is now take three different materials which are semiconductors and have different band gaps. And so this has a band gap which is larger than the one of silicon, so it can take out more high energy photons. And then this one is about a little higher than silicon, but nearly the same. So it also takes out the same kind of photons out of the light, unlike silicon. And this one here, the third one, has just half the band gap of silicon, so it can take out the low energy photons as well. So it can take a whole spectrum of photons, and that brings you to a much higher efficiency than having only a single material with a single band gap here. And so this is called multi-junction or multi-interface solar cell. And it can have a theoretical efficiency of 3 times, so 60%, and in the laboratory already it has been achieved 40%. And this is a basic structure which you use, so 3 types of NP depletion zones. And in between you have these tunnel diodes. Now let me say what that is. A tunnel diode is a wide band gap, so really wide band gap. So it is transparent for all photons. That's important. So photons can travel through these tunnel diodes. No photon absorption, highly doped diode. And the high doping reduces the length of the depletion region. So the depletion region becomes very thin. It's highly doped, but it becomes very thin. And if it's so very thin, then electrons, by their kinetic energy, can tunnel through. Even if it's a relatively high barrier, but they just push through. And in quantum mechanics, they can also compute that, and that's a famous phenomenon of tunneling. So even there's a high wall, but the wall is thin, and therefore the electron can still penetrate. Yeah, that's the reason why you have these tunnel diodes in between here, so that the electrons can go all the way through from here, through here, and come back and leave them behind. And so you understand this is quite a complicated structure, and therefore to use it directly is a waste of money. So what the researchers do, they put a cheap lens on top of here, they concentrate the light, and then they have high intensity light hitting this expensive device and being converted at a very high efficiency. And so this is a standard photovoltaic cell here, just flat silicon modules. And this is the concentrator type here with these lenses on top. And so the efficiency of that is the concentration factor is the collection area divided by the conversion area. So that really adds substantially to the efficiency. It makes things cheaper. And here you see a number of such modules, which are concentrator modules, and they have a high efficiency. And because the sunlight is concentrated and they have a high efficiency, for the same output of these solar cells, you need less area. So on a smaller land, you can make the same amount of electricity like you do with the standard cells on a larger plot of land. Okay, you don't need water, and the energy payback, because they're quite efficient, is only after 6 to 8 months. So you operate in 6 to 8 months, and then all the energy used for manufacturing, for production, is coming back already. And the electricity costs for the electricity generated here from these modules is relatively cheap. So 10 euro cents per kilowatt hour, and 1 euro cent is about 1 yen. So 10 Japanese yen per kilowatt hour is about the price. And there is a collaboration between German companies and research institutes and Japanese companies and research institutes called New Generation Concentrator Photovoltaics, NGCPV. And this is just a Adobe Photoshop combination of Fuji and these concentrator solar cells, just to give you this imagination. And so in this collaboration, it's a first large-scale collaborative project between the European Union and Japan, and the Japan Energy Cooperation Agreement between Japan and the European Union. And it has a lot of funding, 5 million euros from both sides. It makes together 10 million euros. And it is for over 3 years, 3.5 years here. And it has started and will finish in 2014. There are 7 European and 9 Japanese partners. And so the work is always done in collaboration. 1 European and 1 Japanese partner, they work together in this project here. Okay, and now I feature this thin film solar cell. And the thin film solar cell uses another type of material. And this is a type of material which is a direct bandgap semiconductor. So no phonons needed, therefore you can make them a lot thinner. So here you have a P layer, then you have here 2 N layers, and you have the front contact, which is transparent. It's a transparent conductive oxide, one of the miracles of chemistry. And below you have the back contact, molybdenum back contact, and this is called CIS because the material is copper indium disulfide. Copper indium disulfide, and you have a layer here in the end layer of cadmium sulfide as well. This is zirconium oxide, and so the thickness altogether is just 4.15 micrometers, so very thin material altogether. And for the traditional silicon cells, you need 200 micrometers. So this is really thick. Silicon is really thick compared and heavy, and needs a lot of material to produce. Here, just need a very small amount of material. Okay, and the efficiency is 12 to 15%. So this industry here tries to argue, buy thin film solar cells, cheap, not so efficient, but cheaper. And you can just put them on glass and you can operate them. So they bargain with the cost advantage. Less efficiency, but cheap, they say. Okay, now let's talk at the end a little bit about the economy. In Germany, the renewable energy industry has created, first of all, lots of jobs. So if you would study in Germany, you'd probably look, after you graduate, into a job in the renewable energy industry. And this is how the job market, the total job market has grown. From 2004, there were 150,000, and already 7 years later, there were 380,000 workers in the renewable energy industry. And here they are categorized according to the different types of industry. And in the solar energy sector, you have 125,000 places. And to give you an idea what that means for the economy as a whole, it's the total German economy, you know, the biggest industry in Germany is still the car industry, and maybe in Japan too. But the renewable energy industry already has 50% of the workers which the car industry has. So it's also really a big scale industry it has become in Germany. Very important for an economy, obviously. And now this is a so-called price learning curve. How these solar cells become cheaper if you increase, if you, for example, double the production. And it is on a double logarithmic scale, then the curve becomes linear, it becomes a line in this scale here. And this slope here means that every time you double the production, the price has dropped in average, there is some jumping here, by 20%. So that means it's really meaningful to go big scale, because then it really becomes substantially cheaper over the years. And this is a diagram showing you the learning curves of the other renewable energies. This is concentrated thermal solar power, which is another technology, directly using the heat of the sunlight. This is a photovoltaic learning curve, which we have talked about already. And this is the wind power learning curve, using wind power generators, wind turbines. And you see, photovoltaic has the biggest slope. So it started out as the most expensive technology, but after a few years, it will even hit the wind power line, and it will be cheaper, or at least the same price, like wind power in the future. So the learning curve is really something which makes you look forward to the future. You say, okay, in the future we can really afford solar power as much as we can afford wind power. And now finally, everybody worries about the cost. What is the cost for the whole economy, for the whole country? And this is the kind of German numbers. And the curves which you see here are the electricity prices for the private households. They are always higher than the electricity prices for the industry. The industry is a large-scale consumer, and they get electricity discount prices. So this is the price of photovoltaic electricity, how it has developed, here pictured from 2004, already until now 2012. And already the price of the photovoltaic electricity in Germany is the same and cheaper than the price which the private consumer has to pay every day for his kilowatt hour. So already the solar electricity in Germany helps to push down the electricity prices on the market. Now these old prices here, for 20 years, they will still keep the electricity bill for a scale of 20 years, 10 to 20 years, at a relatively high level, because these old prices here were guaranteed by the government to go into mass production and to get down to the cheap prices. But once these guarantees are expired, then we have a cheap source of energy which will be really down here, somewhere in a few cents per kilowatt hour. And that was the reason to introduce this program to guarantee the prices at the beginning here. And you see, soon the prices of photovoltaic electricity will be at the same level like the industry electricity prices and below. So for the future, this is really the strategy to get the energy prices down, and this is good news for the consumers and good news for the industry in the future. Okay, thank you for your attention. That was my presentation. If you have any questions, please ask me. Yes?
In the future, is it possible for the solar power generation to take place of the nuclear power generation?
Mm-hmm. Yeah, so the situation which we have now in Japan is that we can switch off the nuclear power stations and we can live only in the summer when we have high electricity demand in the daytime. Everybody wants to use air conditioning, etc., or the lights in the office towers, etc. Then we run into trouble. And then we need to ration the electricity. And then the government tells some industry, oh, please switch off your production in the daytime so that we can manage to have enough electricity for the country. And exactly in the hot summer days, when you have the peak of sunshine, you also get the peak of the solar electricity, which has a very high market value as well then. And therefore, in that sense, the photovoltaic electricity can now be a great benefit for Japan to help Japan live without nuclear power. Because especially in the summer, when there is this high peak demand, there's a strong argument, oh, let's switch on, at least in the summer, a few more nuclear power stations to have enough supply, etc.
Thank you.
Yes, you're welcome. So thank you very much for attention. I guess I don't see most of you before Christmas or before the New Year. So at the end, I wish you a Merry Christmas and Happy New Year, and see you again next year. Okay.